Now it's time to address RLC circuits and see what happens when we throw all of the elements together. So suppose we have an AC source and we have a resistor, we have a capacitor and an inductor all in series. Okay. Now, the very first thing to note is even though this is time varying with a sinusoid, instantaneously, Kirchhoff's loop rule is still true. So the source voltage instantaneously has to equal the potential across the resistor plus the potential across the capacitor plus the potential across the inductor, right? But remember that for the resistor, our current is in phase. For the capacitor, the current leads the voltage. And for the inductor, the current lags behind the voltage. Okay. Now, the potential across each of these elements, by the way, has to be proportional to the resistance for the resistor. It has to be proportional to the capacitive reactance for the capacitor. And it has to be proportional to the inductive reactance for the inductor. All right, so here's where your phasor diagram really becomes important. Okay. So at any generic time, all right. Oh, by the way, well, this is true for all time. These potentials will be proportional to these, but their actual values will vary sinusoidally, but their RMS values do not. Okay. So it will also be true that VRMS from the source must equal the RMS voltage across the resistor plus the RMS across the capacitor plus the RMS across the inductor. And this is true for all time. Okay, so if my current at a particular time is right here, okay, then what that means is from these statements, the voltage across the resistor is in phase. And then the voltage across the, let's use green. The voltage across the inductor will lead the current, or your current lags the voltage. That's another way of saying that. And your voltage across your capacitor will lag your current. Okay? So, with this in mind, because each of these potentials is proportional to their reactances and resistances, this means that we can draw another diagram. Now, what we're going to do is we're going to suppose that we've rotated this by 270 degrees. Okay? So suppose, do we want to rotate it 270? Actually, let's rotate it. Oh yeah, 270. Yeah. So, if we rotate this 270 degrees, then what we will have is our potential. Well, actually, our capacitive reactance will be down this way, and our inductive reactance will be pointed here. And I really should label this. So this is going to now be chi sub c. This is going to be chi sub L. And our current and resistor are going to be along the so-called x-axis. So our current is here, and our resistor is here. Okay. So I'm just using these relations to transform this phasor diagram from voltages and current into reactances and resistances and current. Okay. So what we're going to do now is we're going to define impedance. So impedance is the total effective resistance in an AC circuit. Okay. So again, we don't call it resistance because these are not just pure resistors. You might have a resistor, of course, that's what the L stands for in RLC circuit, but you can have inductors and you can have capacitors, and so they are not resistors, but they can behave like it. So their total combination will allow you to use or calculate an effective total way that your current is quote unquote impeded by this combination. Okay, so here we go. If we look at this phasor diagram, okay, what we can do is if I look at this chi sub L, now it doesn't have to be true that chi sub L is larger than chi sub C, but it will always be true that chi sub L leads chi sub C as far as the current goes. Okay? So what we can do is if our reactances and our current and resistance are along these axes as shown, then we can make a total reactance by the vector sum of our chi sub L and chi sub C. But since chi sub C is always going to be opposite chi sub L, then the vector operation is to subtract these. So this will give us a reactance. Let's use, we're running out of colors, but it's okay. We used purple before. Let's use this plume. Hopefully we can differentiate it from red and pink, but in any case, okay? So this represents chi sub L minus chi sub C, right? And our resistor is going to be here. And so your total effective resistance, or the total impedance in your circuit, is now the vector addition of these. And that vector addition is this vector right here. So this is what we define as the total impedance Z. Okay, so by this diagram, we can see that Z is equal to the square root of R squared plus chi sub L minus chi sub C quantity squared. Okay? And by that same token, therefore, your RMS current in this circuit can be found by taking your RMS voltage and dividing it by Z. Okay? And so, as a result, this is just Ohm's law applied to this total circuit. Okay? Okay? And notice that we're basically using all of the principles we've used before. We're using Kirchhoff's loop rule here. It's just a series circuit, so we don't have to worry about junction rules. Now, of course, you can arrange these elements in various complex ways. There's no question of that. You could put these in parallel and have two elements in series and one of the elements in parallel. You could have multiple elements in parallel. You could have multiple capacitors, multiple resistors, and multiple inductors. Who cares? But the bottom line is that for the simple RLC circuit case, this is how you calculate the impedance. Okay? But if you look at this denominator, let's look at this in a little bit of detail. This is not dependent on omega, but this is. And so, therefore, Z is a function of omega. All right? So your total impedance will change as you adjust the angular frequency. Okay? Now, let's actually write out what these formulas are. So chi sub L is L times omega minus 1 over C times omega. Okay, and this quantity gets squared. So let's kind of think about how Z behaves if I have really, really small omega. Okay. So if omega is very, very small, then chi sub L is very small, but chi sub C is very large. So for very small omega, it becomes approximate that this becomes r squared plus chi sub c squared. Okay, because chi sub c, or your capacitive reactance, is going to overwhelm your inductive reactance, right? And this is what was argued in the previous video, right? So, if omega is small enough, then this goes to infinity. So therefore, z of omegas that are approximately 0 is very close to 0. And then on the other end, if omega is very large, we can use the exact reverse argument. Chi sub L is large, and chi sub C is very small. So therefore, z as a function of omega becomes approximately r squared plus chi sub L squared. Okay? And so, once again, if omega is large enough, then chi sub L will approach infinity. Oops, I didn't mean that the impedance here is 0. I meant that the impedance is nearly infinite. It's the current that will go to 0. So let me correct that. So in that case, your impedance will go to infinity. Okay, so in both of these cases, your impedance approaches infinity. Okay, so in the case where omega is close to 0, your impedance is nearly infinite. And in the case of really, really large omega, it's also approximately infinite. So what that means is if you start your dial for your impedance at 0, your impedance will be nearly infinite. But then as you increase omega, it will decrease to some local minimum, and then it will get larger again as omega gets larger. So your impedance will look something like this. Okay? So it'll start out really, really high, it'll decrease, and then it'll reach a local minimum, and then it will then increase without bound if you have some sort of method with which to just constantly increase your angular frequency, and your impedance will continue to grow. But what we're interested in is this point right here. Okay? What this means is, if I apply this to Ohm's law, okay? Abbreviated, if I is equal to V over Z, then what this means is that if Z is really large, I must be really, really small. Oop, I'm not plotting Z anymore, I'm plotting I. So your current will start out at 0, grow to some maximum value, and then die off again. Now the exact shape of this is going to depend on the values of your resistor, capacitor, and inductor. But this is the general idea, okay? So the peak in your current, where your current is maximized, corresponds to when your impedance is lowest. Now, again, there's no upper limit. Your upper limit is just bound by what your angular frequency can achieve, either way, really, really small values or really, really large values. But there will be a minimum for your impedance, and that means there will be a maximum for your current. Now, what this implies is when will Z be minimized? This is fixed. Your resistance is fixed. This is omega dependent. So here's the question. Obviously, the true minimum of Z will occur if, well, let me put it this way. This will occur when this quantity equals 0. Is there an angular frequency for which this term drops out? In other words, at which point the reactances have the same value. And so if you come back to the phasor, okay, if these have the same value, then there won't be any length along the y-axis here, and your total impedance just lies along your resistance. So this is when Z will be minimized. So let's calculate this. So this is L omega minus 1 over C omega equals 0. That means L omega equals 1 over C omega. And therefore omega squared is equal to 1 over LC. And omega is equal to the square root of 1 over LC. This is just the frequency from the LC circuit that we saw previously in an earlier chapter. But here, this is what we call the resonant frequency. Okay, so this is the resonant frequency. And we call it the resonant frequency because it's the frequency at which your current is maximized. Okay, it's the current at which well, let me put it this way. It is the omega at which z equals r. Okay. So this resonant frequency is the frequency it's the angular frequency that maximizes the current. Okay. And we can even translate this to the regular frequency by the fact that omega equals 2 pi f. So f is equal to 2 pi, or omega over 2 pi. And so your resonant regular frequency is equal to 1 over 2 pi times square root LC. Okay. So what happens at this point is the capacitive reactance and the inductive reactance have reached a balance where they have the same magnitude. And as a result, because they are 180 degrees out of phase with one another, they basically disappear. And therefore, your reactive, or your total impedance, rather, just goes to your total resistance, okay, whatever your R value is. And this is the regular frequency at which this occurs. And the reason that we like to use this formula sometimes is because most function generators allow you to control F rather than omega. You're just changing the hertz, not the radians per second. Okay, so with that in mind, right, you now have the way to calculate your RMS current, and you can calculate what the resonant frequency is when these reactances cancel out. Now, there's one last thing to note, and that is what we call the phase angle. So let's redraw this phasor. So if I have two vectors, my resistance here and chi sub c, L minus chi sub c here. Okay, and my resultant is right here. Then this angle right here, we usually use phi, so let me change that from theta to phi. Okay. So this angle phi is what we call the phase angle. And it represents the angle at which the total impedance makes with the current. And remember, your current will always be in phase with your resistor. Okay, So this total impedance does not necessarily have to be in phase with your current, but when you're looking at your RMS values, you will always be able to calculate the same phase angle, right? And so what angle is this? Well, if we use trigonometry and make a right triangle here, okay, then what I have is that tan phi is equal to chi sub L minus chi sub C as one side of your right triangle divided by your resistance, right? So this is just opposite over adjacent, okay? And so phi is then equal to the tan inverse of chi sub L minus chi sub C over R. Okay, so this is your phase angle. Now the phase angle is going to play a very important role when we talk about things like power and so on and so forth, which will be coming up in the next video. But that is how you calculate the phase angle between your components. Okay, so that wraps up RLC circuits, the basics anyway, how to calculate the total impedance, the resonant frequency, and the phase angle. And we will talk about power in the next video.